Okay, we've come to the end, my friend. One last thing to do. The procedure says to determine the percent yield of your product. Percent yield. Are you kidding me? This is like 24 points in the lab report, so we gotta get this right. How do I do a percent yield? There's something from chapter 3 in the back of my head that says, I've done those. Percent yields require you to do what first? Ooh, yeah, theoretical yield. What's theoretical yield? That's the maximum obtainable product. And what are theoretical yield calculations based on? Oh, yeah, limiting reagent. All right, so now I got to determine the stupid limiting reagent. Hey, listen, let me just tell you a little secret here. The limiting reagent for this reaction is your nickel. You could argue that one way or another, but this is an aqueous solution and the excess of that washes out. So your limiting reagent really is the amount of nickel 2-sulfate hexahydrate that you started with. So then if that is your limiting reagent, and it is, how much of that did you start with? Go way back. You remember this from a long time ago? We started this whole thing with 0.940. Find that in the data table. That's the very first thing in the data table was how much nickel 2-sulfate hexahydrate we weighed out. 0.942 grams, right? Remember, this is the amount of product that we made. We didn't know what the product was when we first made it. Now we do. That's how much we made. So this is what we started with, and this is our limiting reagent. So let's start the calculation with the limiting reagent, as we always do in these types of problems. So I'm going to go way over here to see. Yeah, good. 0.942 grams of nickel 2-sulfate hexahydrate. That's my starting. Oh, this is going to be a long one, right? So now what? I want to get rid of grams of nickel 2-sulfate hexahydrate. You know how to do that, right? Grams of nickel 2-sulfate hexahydrate are to moles of nickel 2-sulfate hexahydrate. What is that relationship? 1 mole of any substance continues to be equal to the molecular weight of that substance. So we're going to have to figure that out. Hey, by the way, here's a little helpful hint. They often write these molecular weights on the bottle itself. I don't know if you see that. They write the molecular weight on the bottle itself. Turns out the molecular weight for this starting material, by the way, it's not hard for you to add up a nickel, a sulfur, 4 oxygens, and 6 waters. You get something like 262.849, something like that. That's what I got with the particular periodic table that I used when I did that calculation. Okay. And we're all okay to do this on one line, right? That this would be in parentheses 1 mole of nickel 2-sulfate slash this, right? All in one. And then what would the next step be? I got to get rid of moles of nickel 2-sulfate hexahydrate to moles of the compound that I made. Remember, what I made was this species right here, right? It was nickel 2 ENs Whew, that's a long complex, right? All right, you tell me, what is that mole-to-mole ratio? How many of these can you get from a nickel 2-sulfate hexahydrate? What's it look like to you? By the way, we're all going to have this number. We're all going to have this same mole-to-mole conversion. What is that? Looks like one of those will give you one of these. Oh, my grandma could do that conversion, right? All right, now what? Now I got to get from moles to grams. This is the hardest step. And when I grade lab reports, this is more than half the problem, this next step. All right, the next step is got to get from moles to grams. So 1 mole of same complex. Did you catch me writing a 6 right there? I caught my mistake. 2 waters, okay? So 1 mole of any substance continues to be equal to the molecular weight of that substance. Oh my word, I've got to figure out the molecular weight of the complex that I made. Actually, that's not that hard to do, right? I add up a nickel, a couple of ethylene diamines. I know what the molecular weight of the ethylene diamine is. I add up 4 waters and a sulfate. And when I do that, I get a pretty big number. It looks like 347.01156. 347.01156. By the way, are we all going to have this same molecular weight? No, we're not. Can I give you a little helpful hint here? When we grade your lab reports, we look at this conversion to see if you were smart enough to know to use the molecular weight of your compound, or whether you just copied the numbers we gave you and you threw 347 in there. If you threw in 347, it means to us you really just don't know what you're doing, right? You have to calculate the molecular weight of your compound to go in there, not the compound that I gave you as an example to follow, right? So your molecular weight, by the way, you get that wrong, I'm going to bleed all over you, right? So get that right. That cancels nicely. And again, are we all okay of doing this in one line, right? This would be in parentheses, slash between those two. This would be in parentheses next. 1 mole of that, slash 1 mole of nickel sulfate, parentheses, 347 point, whatever the molecular weight is, slash 1 mole, right? We've done enough of that to where it should be kind of almost second nature. All right, woo! What does that equal? Go ahead and run that number for me and tell me what you got. Yeah, I got like 1.2436223. Did you get that number? 1.2436223? Yeah. What is, by the way, the correct number of significant figures here? Based on what? How much you weighed out. So what would be the correct number of significant figures in this particular example? It would be what? 1.24 grams. Would be 3 sig figs, right, based on that right there. Hey, let me ask you a question, just to make sure that we're still good. Check this out. Are you listening? What if I was just over a gram, 1.035 or something like that? If I was just over a gram, would I still have 3 sig figs here? No, I'd have what? That's right, I'd have 4 sig figs. Okay? So we're going to look for that because some of you are going to get data with only 3 sig figs of starting material, and some of you are going to get data with 4 sig figs. And we're going to see if you actually know how to do significant figures at this point, and you actually should. All right, now what is this number here? That is the theoretical yield. The theoretical yield is what? That's the maximum obtainable product. You can't get more than that. You almost never get that much. You always get less because all reactions don't go at 100%. Here's something that's interesting. The number of different compounds that you get, some are fairly high yield reactions and some are fairly low yield reactions. So don't get all worked up if you get a fairly low yield. That's common for one of these complexes, believe it or not. And there's a couple of complexes that give you a pretty high yield. Okay, so how do I get percent yield from my theoretical yield? You know how to do that. Percent yield is always, it hasn't changed since chapter 3. Percent yield is the grams of complex obtained. It's the grams of your nickel EN complex obtained. Get rid of that molecular weight. Divided by grams of the nickel EN complex that is theoretically possible, the amount, the theoretical yield, that number, right? And then to get a percentage, I always do what? Times 100. So what are these numbers? Almost out. Oh, I got. Let me do this. Let me do this. Okay. Percent yield. We're going to finish it out. How much grams did I obtain? You got a number? Can you look at your data table and get me a number? Yeah, you got what? Where is that? That's this number right here, right? That's how much you actually made, 1.048. So you have 1.048 grams of that complex nickel, yen. Boy, I'm getting tired of writing this. Divided by, right? What? The theoretical yield. This number, I don't use 1.24. I use the 1.2436223, the number that's stored in my calculator, so I don't get rounding errors. Grams of, I'll have to write it one more time. Final step. Times 100. Now, tell me about what happens with units. Units. Is it not true that grams of the complex cancels? And anytime I have a percent yield, the answer comes out to be what? Unitless. Unitless. So, what did you get to the correct number of significant figures? I know that you got 84.26995, but is that what you're going to write down? The correct number of significant figures is 84.3%. 84.3% yield. Again, some of these complexes have fairly 84% yield is pretty good. Some of them are 60 to 80%. Some of them are actually in the 40%. There's one of these complexes that's like 25 to 30%. You're not going to be graded on what percent yield you got. It's going to be, can you run the numbers correctly? All right? That brings us to the end of the longest, hardest. You're going to have to be the most disciplined on this particular lab report. It's going to take a great deal of effort on your part to get all this together. So it's a 200-point lab report. We made it worth twice what a regular lab report would be because it takes, like 4 times longer to write the whole thing up. But it's one of the most interesting and coolest experiments we actually do. Okay? So that brings us to the end, and we will see you on the very last lab report, calorimetry, coming up next. We'll see you then.